In this video, we will look at a few more problems associated with magnetic force exerted on a moving charge. We will see how motion of a charge can be analyzed when the charge in question is moving in a region where both electric and magnetic fields exist, namely the cross fields. We will also do some vector calculation associated with magnetic force on a moving charge. Problem 1. A particle with an initial velocity of 4,000 meters per second in the direction of I hat enters a region where both uniform electric and magnetic fields exist. The magnetic field in the region is given by this expression. The magnitude is 0.5 Tesla in the direction of minus j hat. Find the electric field in the region if the particle passes through undeflected and its charge is given by that much coulomb. Now repeat the calculation if the charge is a negative charge with the same amount of coulomb. So let's do the calculation for the positive charge. So you have a positive charge and it is moving along the positive x-axis because the direction of its velocity is I hat. So the velocity is given by 4,000 meters per second in the direction of I hat. Note that the magnetic field is vertically downward. So that is the magnetic field. The magnitude is 0.5 Tesla in the direction of minus j hat as given by that expression. We need to pinpoint the electric field. What is the magnitude and the direction of the electric field so that this charge moves undeflected, meaning it goes along a straight line. Now when we say undeflected, that means the net force on this charge has got to be zero. That is the basic concept. So how many forces are there that contributes to the net force? The first is the magnetic force, and the second is the electric force. And the vector sum has got to be 0. For these two forces to cancel each other, their magnitudes must be the same and their directions must be opposite to each other. So let's look at the directions of these two forces, starting with the magnetic force. Magnetic force is given by the following expression: charge, the cross product of the velocity vector, and the magnetic field. So in this case, the velocity vector is quite simply the vector u. So let's apply the right-hand rule to this expression. When you curl your right-hand fingers from the vector u to vector b, you will notice that your right-hand thumb would be pointing inward into the plane. So the direction of the magnetic force is therefore represented by that cross. The direction of the magnetic force is going into the plane. So that is the direction of the magnetic force. And the magnitude of that magnetic force is quite simply the charge times the speed times the magnitude of the magnetic field. Note the direction between u and b is 90 degrees, so sine 90 is 1. What that means is, for the net force to be 0, the electric force must be coming out of the plane. That's represented by this dot. And we know the expression for electric force is given by the charge strength times the electric field vector. So since we're dealing with a positive charge, and we require the electric force to come out of the plane, then the electric field direction must also come out of the plane, like that, represented by the dot, with magnitude given by that expression. Since the magnitudes must be the same, we can equate those two expressions. We get QE, magnitude of the electric force, equals magnitude of the magnetic force, Q times 4,000 times 0.5. So the Q cancels, and you can find the magnitude of the electric field to be 2,000 newtons per coulomb in the direction out of the plane. So if this is the x-axis, that is the y-axis, the direction out of the plane is the z-axis. So we can write the expression for the electric field for the first case to be quite simply 2000 newtons per coulomb k hat. What happens if the charge is now a negative charge? So you have a negative charge moving in the same exact magnetic field. Now, since the charge is negative, the magnetic force, which is given by this equation, will now point out of the board as represented by this dot, because now Q is negative, so it should be opposite to the case with a positive charge. So what that means, the electric force should be going into the plane, and we know the electric force is given by Q times electric field. Now, if this charge is already negative, and we know a negative charge would move opposite to that of the electric field, then the electric field should also come out of the board, as represented by this dot, so that the electric force it exerts on the negative charge will completely cancel the magnetic force created by this magnetic field on that negative charge. So as before, equating the electric force to the magnetic force, where the charge cancels, you see that the magnitude of the electric field is still 2000 newtons per coulomb, and still in the same direction as before, namely in the direction of k hat. And that solves the problem. Problem 2. A positive charge Q with mass 1.5 times 10 to the power minus 14 kg is moving through a region with uniform magnetic field, given by this expression. At a particular instant, its velocity is given by that expression, the vector expression. The magnetic force on the charge is 2.5 newtons in magnitude. Find the strength of that charge, Q in coulombs, and determine the cyclotron frequency of the charge. We know the magnetic force is given by the following expression. Velocity, cross product of velocity and the magnetic field. So let's look at the right-hand side of this equation. Q, let's write down this vector product in determinant form. I, J, K, those are the unit vectors. The velocity vector has all components. So this is 4, the x component, minus 2 is the y component, and 10 is the z component. Now don't forget that 10 to the power 6, the common factor for the velocity, and you can write that out of that determinant sign. The next vector is the magnetic field. The magnetic field is given by that expression with only the z component. So the x component is 0, y component is 0, and the z component is minus 0.25. So let's bring out the common terms out of that determinant sign, and let's expand the determinant. So the I component of that force vector can be calculated in a usual manner, as we do for any cross product. So that's going to be this times that minus this times that. So it's going to be 0.5 minus 0. Next, the j components, or the y components, can be determined by crossing out the j hat in two mutually perpendicular directions. So this times that is 1, it's actually minus 1, and this is 0, so it's minus 0. And the k hat, when you cross out the k hat in two mutually perpendicular directions, this times that is 0, this times that is 0, so it doesn't contribute, there is no k hat. So you see that the right hand side is q times 10 to the power 6, 0.5 I hat plus j hat. So let's compare the magnitude of the left hand side and the right hand side. Now we know the magnitude of the force is 2.5 newtons, so we equate the magnitude 2.5 to the magnitude of this entire vector, which in this case is q times 10 to the power 6. The magnitude of a vector is computed in the following manner: sum of the square of the components, like that. And from this equation you can solve for the charge, and it will turn out to be 2.24 times 10 to the power minus 6 Coulomb. So that's the answer for part A. Now for part B, which is the cyclotron frequency, it's given from a previous video. You'll find that it's given by the charge magnitude times the magnetic field magnitude over the mass of that charge. The charge strength is given by 2.24 times 10 to the power minus 6. That is what we have determined in part A. The magnitude of the magnetic field is given by that expression, 0.25 Tesla, and the mass of the particle is given there, which is 1.5 times 10 to the power minus 14 kg, and it will give you an answer of 3.73 times 10 to the power 7 radiant per second. And that solves the problem. Problem 3. A particle with charge 6 nanocoulomb moves with a speed of 2 times 10 to the power 4 meter per second along the positive z-axis in a region of uniform magnetic field. As a result, there is the magnetic force of this much newtons exerted on it along the positive x-axis direction. What is the uniform magnetic field in terms of magnitude and direction? So as before, the equation to use is F equals to Q, velocity vector cross into the magnetic field vector. Now we know what the force is. The force is 4 times 10 to the power minus 5 newtons in the direction of I hat, the plus x-axis direction. Now let's expand the right-hand side. Charge is 6 nanocoulomb, so 6 times 10 to the power minus 9. Let's write the vector product in determinant form, ij k hat. The velocity vector has only k hat direction, so there is no x component and no y component, but there is a z component. 20,000 positive, because it's moving in a plus z direction. Magnetic field we don't know, so for now let's simply write all the components, bx, by, bz. Note that the force is purely in I hat direction. So if you look at the I hat direction, crossing out I hat in mutually two directions, in two perpendicular directions, you see that this times that is 0, minus this times that. So the I hat component is quite simply minus by times 20,000. What about the component, the y component of the force? Now we know there should not be any y component because the force is given by that expression, so it should be 0. So what that means is, as you cross the j hat in two mutually perpendicular directions, you get this times that, 0 anyways, minus this times that must be 0. So that means bx has got to be 0. So the magnetic field has no x component. And it should not, the force should not have any z component as well, because again, the force is purely in an I hat direction. So if you cross the k like that, this is 0, that is 0. So we can take the bz to be 0 as well. And that is reasonable because cross product of two vectors, one vector being along the z direction, the other vector being along the y direction, should give the resulting cross product in an x direction. So it's reasonable to assume that bz is 0. So equating this number to this expression, you should be able to figure out the unknown by, and that will be negative 1/3 Tesla. So the vector expression for the uniform magnetic field is minus 1/3 Tesla j hat. So the direction of the magnetic field is along minus y-axis with a strength of 1/3 Tesla. That solves the problem. Thank you for watching.